Final talk for the session is going to be by Andrew Rechnitzer, who's telling us about the trials and tribulations of preserving topology. So, Andrew, I'll hand it over to you.
There. I hope people can hear me now. Does it work?
Yeah,
Nathan?
That's great. Thanks, Andrew.
All fine.
Okay. So I guess I'll start by thanking the organisers for putting this together in this day in memory of Richard Brak. He's someone I've known for, I guess, pretty much most of my mathematical life, and I miss having him around. Even though I'm over here in Vancouver, I was hoping to be in Melbourne at this time of year, and Richard would have been high on my list of people to have coffee with and so forth. So thank you very much to the organisers for putting this on. So the work I'm going to talk to you about is work that is ongoing and has indeed been ongoing for far too long. And it's work with Nick Beaton and Nathan Clisby, who have been very patient with me, taking far too long and so forth. But it's work on the idea of how do you preserve topology or sample given topologies preserve topologies while you're sampling self-avoiding polygons. So roughly, if we go up to a very, very high level, one of the key questions we'd sort of like to answer in this game of the intersection between walk models and topology or statistical topology, I guess, is how does the topology influence the geometry of the objects that you're looking at? So a good example of this is, what does a trefoil look like? So this came up in Chris's talk, and she focused in on this idea that somehow we expect the trefoil often to be much smaller than the rest of the polygon. So so what does a trefoil look like? And if you think about this for a little bit, you realize that you need to answer the question, well, which trefoil? And so, there's lots of different ways of looking at this problem. And so, you need to put some sort of probability, some sort of distribution on your set of closed curves. So you need to define a probability measure on the set of closed curves in R3. So, when you've done that, you can use that measure to study what a typical trefoil looks like under this measure that you've chosen. And so two measures, one of which I've played with for a very long time and one that I'm getting to know, how hard can this be? I mean, really, we've been playing with self-avoiding polygons. We know about random polygons. How hard can it be to define this measure and do things with it? Well, my two favorite measures that I'm used to playing with, and indeed self-avoiding polygons, I was introduced to in Melbourne way back in the mid-90s. We take a loop and we make an embedding of that simple loop into, say, the cubic lattice, and each embedding we decree to be equally likely. So each embedding of length n is considered to be the same probability. So we have one here bouncing around, which I hope works on Zoom. And then another one, probability measure that I'm getting to know a bit better and starting to enjoy playing with, is the set of equilateral random polygons. And here, each edge has unit length, and each direction of the edges is chosen uniformly on the two-sphere and conditioned so that the thing actually closes up. And so here's a equilateral random polygon here. And one of the things that you should perhaps notice almost immediately is that the self-avoiding polygon that I've chosen here, which is roughly speaking has been chosen uniformly, is quite open and bloated, whereas the equilateral random polygon I've chosen here is much, much more compact. And this is something that we would expect. Okay, so that once we have these two measures, we might try to prove some stuff about what the topology looks like. And you realize very, very quickly, and it's perhaps no surprise to the people in the audience there, that analytic results in this topic are hard. They're very hard. And there's a great deal of very, very nice, interesting work by people like Stu, who's in the audience here, DeWitt Sumners, Ken Millett, Chris Soros, Bucks, Enzo Anandici, Deguchi, Cantarella, and so forth. There's a very large literature on this, each people trying to eke out some rigorous analytic results here, and as well as a whole bunch of numerical simulations. And there's some, I can point you at a nice review article here if you are interested in more. And of course, because analytic results are really hard, we resort to doing what we can, and often what we can do is some random sampling. And there are sort of two methods that you might use here if you're trying to sample polygons with a given topology. So if you want to get at trefoils, polygons which encode a trefoil, is that you might sample a superset, namely a whole bunch of polygons, some which might be trefoils and some which might not, and then sieve out the ones that you want, so that you might do lots and lots of samples because it's very quick to sample from the set of all polygons, say, and then check to see which ones are trefoils and pull those out and study those. So that's one way you might do it. The other way you might do it is you might try to set up your sampling algorithm so that it only samples curves of a particular topology. So you only sample within the space of trefoils, say. Okay, so these are two very, very broad approaches here, and I'm staying very, very high level and for as long as I can. Okay, so if, for example, if you're trying to do this first approach of sampling a superset of trefoils, so superset of polygons, and then sieving out, well, one way you might do that in the space of equilateral random polygons is you might use this very, very nice algorithm due to Jason Cantarella and others, which allows you to do exact random sampling of equilateral random polygons in time, big O of n to the 5 halves. And that produces a completely statistically independent polygon. So you can do that. You can sample very large, very quick equilateral random polygons. Another way you might do it is that you might pivot on self-avoiding walks. So you take your favorite self-avoiding polygon and do pivots on that. And the pivot algorithm for that goes back to Lie, and then very, very beautiful work by Madras and Sokol showing how powerful, how good it is. And then, at the risk of bringing coals to Newcastle, so to speak, there's this wonderful implementation by Nathan in the audience there, which allows you to basically do samples in log n time, so that it's sort of faster to do a sample than it is to write down the object. And so this works very, very simply. I mean, not the Nathan implementation, but the pivot algorithm works very, very simply, that you take your favorite self-avoiding polygon, you pick a couple of vertices on the polygon that splits things into 2 segments, and you look at one of these segments here, usually the shorter one, and you do some symmetry operation to transform it into some new configuration like that. And if the result is a self-avoiding polygon, you keep it. And if it's not, you reject it. And so this gives you a very nice Monte Carlo algorithm, which fails a lot, but it fails quickly. But when it succeeds in making a very, very big change to your conformation. Okay, so in both of these cases, you can sample from the set of either equilateral random polygons or self-avoiding polygons. You can do that very, very quickly, but you have no control over the topology during that sampling method. And so then you have to actually test your various samples to say, hey, is this a trefoil or not? And unfortunately, that's hard. So you can define that to be hard in some much more strict, rigorous sense. But basically, the not invariants you might use to say, hey, this curve that I've got is actually a trefoil, or at least I'm pretty sure that it's a trefoil, those things are very slow to compute. Okay, so this has some problems, and it gets worse as the polygons gets longer, because polygons of a fixed topology become exponentially rare as the size of your polygon gets longer and longer and longer. And the result goes back to DeWitt and Stew and Pippinger back in the late 80s at about almost, I think the result happened at pretty much the same time using pretty much the same techniques. And so this means that if you're trying to sample large polygons, you're going to be trying to get at an exponentially small space. If you're trying to find just, say, the trefoils, the space in which you're trying to sample is much, much bigger than the things that you're actually trying to get at. And so it's going to slow down exponentially just because the superset is so much bigger. But also the process of testing is going to be incredibly slow. So this sampling of supersets and then extracting out the ones that you want becomes very, very difficult as polygons become longer. And indeed, identification becomes a substantial bottleneck. You have a long polygon, it has many crossings, and that makes it very hard to identify. So as an aside, one might try to understand if you do have a very, very large polygon with lots and lots of complicated topology and entanglement, is there some sensible way to measure the trefoilness of that very large complicated mess, which is certainly not a trefoil, but is there some way that you can actually decide if it's trefoil-y or some measure of how trefoil-y it actually is? That's a question that I'm thinking about in the background here. All right. So the other thing that you can do, because sampling from this superset and getting out the ones that you want is really, it becomes very, very slow as things become very large, is you can you can study things of only a fixed topology. And so the standard way of doing this is to use a Markov chain on self-avoiding polygons of fixed topology using BF-ACF. So there's no topological testing needed because strand passages aren't possible. You can't change the topology when running this algorithm. And it's been proved originally by Van Rensburg and Whittington that this is ergodic on knot type when you run this on the simple cubic lattice. And then later Bucks and I proved this for the FCC and BCC versions of this algorithm, leaning very, very heavily on this result here. Okay, so this works just by making little local deformations to the polygon. And you can start with a small conformation of a fixed topology and then deform it using local moves, which just do these little local conformation changes, and you can tune it so that it grows to become larger and shrinks to become smaller with equal probabilities. There's all sorts of optimizations you can do here, but roughly the problem with this is that it makes the Monte Carlo algorithm, when it's tuned very well, makes a random walk in the length of the polygon. So it's trying to do this growing and shrinking, so it looks a bit like Brownian motion, just in the length of the polygon. And so it can take a very long time to make independent samples of long polygons. Because it is doing this random walk in length, to get out to, say, length 1,000 takes n squared successful moves, or n squared moves, order n squared moves. So it becomes very, very slow as the polygons become larger. So again, you run into this slowing down of these approaches, both the sampling a superset or sampling fixed topologies. They just become very, very slow as the polygons become longer. And this is really a bottleneck for research in this general area. Okay, so another thing you can do with fixed topology is you can do some sort of restricted pivots. So there's a way of doing this, which goes to a paper by Zhao and Ferrari, where you attempt to pivot one chunk of your polygon, you attempt to pivot into a new position, and you look at the surface that to the original segment and its pivoted version, look at the surface that maps out, and the pivot, you decree it to fail if some other edge crosses that surface. Now, the way that they set this up was extremely computationally intensive. And so they decreed that, well, we're only going to do this for short segments. So we're only going to allow pivots where the polygon is where the pivoting segment is quite short. And indeed, they only allowed pivot segments of up to length 5. And they did some strong analysis of this, and they said that this is probably okay and that it actually works pretty well for the moderate length polygons that they were looking at. But we know, due to work of Madras and Sokol, that no local update only algorithm can possibly be ergodic on the space that you want. And so while this works probably okay for moderate polygons, they couldn't push this segment length long enough so that it can work for very long polygons. Okay, so that algorithm is a nice idea and is this sort of the starting point of what I want to do here in order to try to speed things up. So what can we do to try to speed up this process of sampling polygons of fixed topology? And so we revisit pivots again, go back to look at the pivot algorithm again, thinking quite hard about that work of where are we? Of Zhao and Ferrari. Okay, so we revisit pivots again. And so one of the things that helps in this is to not think of the pivot algorithm as literally taking a chunk of your polygon and pivoting it, but just to think of a pivot as being any continuous deformation of your polygon from its initial configuration to its final configuration. And this helps. We're also going to use the Clisby method, I guess I will call it, the Clisby method for very, very fast pivots, which requires us to store the polygon and its symmetries in a very careful binary tree. And part of the game there is what you might call lazy evaluations of observables, namely you don't actually want to write down the polygon that you're pivoting. You want to compute as little as possible. And indeed, this Clisby method, there's a very close link to some work done by Jason Cantarello, who built this equilateral random polygon sampling algorithm. There's some very close links there between the way Nathan's method works and the way that Jason Cantarello's sampling algorithm works. There's a lot of interesting parallels there. Okay, so there's two sorts of pivots that I want to consider. One is what I call an inner pivot, which is the standard thing that you do in the pivot algorithm. Namely, you pick some pivot segment and you do a symmetry operation which, if you're trying to preserve topology, can really only be rotations. You pick it and you pivot it. Okay. The topology checking, the way that we do this, and I think this is something that that Richard would have enjoyed. So when you do that pivot, you have a starting position of each edge and a final position of each edge. And that edge, as it moves from its initial position to its final position, maps out a twisted quadrilateral. And you check the intersection of that edge with every other edge in the polygon by triangulating that quadrilateral. So it turns into two possible triangulations. And we use methods from ray tracing to do that. And in particular, I'm using a very standard technique from ray tracing, this Molar Trombore algorithm for detecting the intersection between a line segment and a triangle. Okay, so there's some very standard bits of ray tracing that you might use here. The other sort of pivot that I thought about is what you might call an outer pivot, where you pick, again, a segment of your polygon and a direction tangential to that, and you drag that segment out to infinity and then do the pivot out at infinity and then drag it back into place. So just another way of thinking about ways of deforming the polygon in order to do pivots. Okay, so we drag the segment off to infinity, we pivot the segment, and then we drag it back. And each of those, we have to do some topology checking. So when we drag something to and from infinity, we have to check for intersections between line segments in projection. And when we do the pivot at infinity, we have to think carefully about these drag lines to make sure nothing intersects them as they pivot around. Okay. Now, if we do a simple, and I use that word advisedly, implementation of both of these things, the computation time, depending on how you want to set it up, is order n squared or order n log n. Picking pivots is order 1, at least on r cubed. On z's cubed, you have to be a bit more careful. Inner pivot, if you do it naively, is order n squared, but maybe as fast as n log n if you code things up carefully. This dragging off to infinity is n squared, or if you use some standard computational geometry, things like Shamus-Hoey, it could be order n log n. Pivot at infinity, just it's an order n check if you do it naively. And then putting everything back together and writing down the new polygon is order n. So this computation time of doing one pivot is going to be order n squared or order n log n, which is not that promising. But hopefully when your pivot algorithm, when it fails, it typically fails very quickly. So you detect the fail before you have to do all of that computation. And when it does actually succeed, it tends to make a very large change to your object. But of course, the proof is actually in the autocorrelation time, so you've got to code it up and see what actually happens. Now, we can Clisbify this. I don't think that's really a word. And the way I always think of this is sort of to think of it by analogy, namely that if you're trying to compute some product of numbers, x to the a, y to the b, z to the c, and the numbers x, y, and z change rarely, but the numbers a, b, and c change frequently, how should you compute that product? Well, the answer is that you should do some standard sneaky logarithmic pre-computation. So when y changes, you pre-compute y squared, y to the 4, y to the 8, y to the 16, and so forth. And then you compute y to the b as a product of those pre-computed pieces, which means that you can compute the new product in time logarithmic in the exponents. So doing this Clisbification of the pivot algorithm requires careful pre-computation and lazy evaluations of things. And so Clisbifying things, we take our polygon and we encode it as a sequence of symmetries acting on a unit edge. And then the position of the nth vertex is just this sum of products of those symmetries acting on that unit edge. And something that really helped me understand how this actually works is to write down a list of the position of vertex 1, vertex 2, vertex 3 as this sort of sum of products. And then you store all of that in a binary tree. And one of the things when you're doing just the pivot algorithm, as it usually is that you can store everything in a nice balanced binary tree where where a leaf node stores the symmetry and a position, and then the internal nodes store the products of the symmetries of the vertices underneath them, and a vector that goes from the first vertex underneath them to the last vertex underneath them. So there's some very nice structure here in this tree that allows you to do a lot of pre-computation and then lazy evaluation if you actually need to find a vertex. Okay, so we can compute polygon vertex positions using these symmetries that we have in the tree and these pre-computed positions. So if we want to compute the position of the fourth vertex, which is the end of the third polygon edge, we can write it down. It's just this sum of products of symmetries. We then look at some of the information we have in our tree. We do some careful bracketing of things, and we realize that it's some of these things that we've already pre-computed. Now, here, this doesn't look like it saves very much because our tree isn't very deep, but if you think about this for a little bit, it requires order tree depth operations, which is log of the number of vertices. So computing the position of a vertex after this careful pre-computation becomes order log n. And if we compute a different vertex, I'll probably just skip through some of this, but you can start to see that it really does speed up what you need to compute if you need to actually find a given vertex. Then when you do some updates, well, what are you doing? You're changing one of these symmetries stored in one of the leaves, and then you have to update things going back up to the root of the tree. And that takes order tree depth operations, which if your tree is nicely balanced, is order log n, okay? So we can do that. And this gives you a very fast Markov chain sampling, the way at least I've set it up here, for equilateral random polygons, because there are no topology checks in anything I've described here. And indeed, if you look at the autocorrelation time of something like the radius of gyration, that's order log n time. And that's much faster than any existing algorithm. The best existing algorithm is by Jason Cantarella, and that takes order n to the 5 halves, but is guaranteed to give you something completely statistically independent. But this algorithm that we're describing here gives you something in order log n time. So indeed, it takes longer to write down the resulting polygon than it did to sample it, which is always a mysterious thing to me. Okay, now it's harder on the lattice because you have to pick pairs of vertices carefully. If you're going to do rotations, those vertices have to lie in various planes in order for that to work okay. Okay, Ian, I think you're drawing on my slides, which is okay. I'm okay with that. But for topology checks, we have to do a lot of extra work involving lots of basic vector and quaternion manipulation. It's very important that you remember to normalize your quaternions at every single opportunity as you do this. There's some nice games with bounding spheres. You have to do a lot of interesting work because you're looking to see when things might intersect. So you have to do intersections between spheres and sphere-capped cylinders. So there's lots of fun games here. You need to check when a line segment intersects a quadrilateral, which is this Molar Trombore algorithm. So there's lots of fun games that you can play with this. And then to give you an idea of how this might work, if you're trying to find, say, the intersection between this L-shaped thing and a chunk of your polygon as it's moving from initial position to a final position, you can take 2 copies of your binary tree and start looking at subsets, chunks of these trees. So in particular, if we have some idea here by looking at this vertex here that I've drawn in red in the top tree, that might encode this orange bounding cylinder, a sphere-capped cylinder, which encodes the bounding sphere around one chunk of the walk and is dragged from its initial position to its final position during a pivot. And then this second red dot on the lower thing might encode the bounding sphere around another chunk of the walk that's fixed during the pivot attempt. And initially, if you look at those two things, you do an order one check to make sure that they don't intersect. And in this case, they do intersect. And so if you find an intersection like that between these, between sets of vertices rather than between individual edges, you refine one of them by checking both of its subtrees. So instead of looking at the whole of that branch together, you refine down to one of the subtrees. And again, you test the bounding sphere of one with the sphere capped cylinder of the other, and you realize, no, that doesn't intersect. And that tells you that you don't have to check any of the vertices in that chunk of the tree, but instead can look at the other chunk. So you look at that chunk of the tree and you see that that still intersects the sphere capped cylinder. And so then you refine down that sphere capped cylinder and you see, oh, hold on, these still intersect. So then you do some more refining. And at that point, I'm now down to the intersection, potential intersection between two line segments. And so I check those using a more rigorous test, namely this Molar Trombore test. Okay. And so does this work? Does this actually conserve topology? Well, it does. Here is a 1024 edge unknot on the cubic lattice after about 250,000 pivots, and it's still an unknot. Okay, so I started with an unknot as a unit square. I did 250,000 pivots on it, and it's still an unknot. And I checked that using this really, really excellent library called Topology, which is a really nice Python library by a group working out of Poland, which is it's a very, very useful library when you're starting to play these sorts of games. And so does it work? Well, again, we can compare the RG histograms of ones sampled by doing what I just described, and then one sampled using, say, pivot. No, what do I want to do? I sample one's using my algorithm and one's using, say, Equilateral Polygon sampler by Jason Cantarella, and then filtering out ones that we can prove to be unknots and check the distribution of RG. And you can see that these are pretty good. They line up very neatly. But is it fast? Well, here you really need to check autocorrelation, and this is research still in progress as we get up to. I actually found that I had a great deal of difficulty computing autocorrelation time. Okay, and I realize I'm running over time. I apologize for that. In particular, I used a couple of different methods. This is very, very nice method of log binning, which I highly recommend people take a look at. And I just couldn't get reasonable answers out of it. And so I plotted the evolution of RG with iterations, and you can see that it's bouncing up and down nicely here, but there's a couple of sort of worrying canyons here. And if you plot more of this evolution, you can see that these canyons are now becoming extremely worrying. And what seems to be happening is that the algorithm is getting stuck in these very compact configurations. And so possibility one is these are bugs in my code. Possibility two is that compact conformations are somehow not so rare. So here's a compact unknot, here's a less compact unknot, and here's a very bloated and open unknot. And so it's possible that these very, very compact unknots are not so rare, and it's very hard to pivot away from them, that most pivots will fail. And this, of course, doesn't exclude possibility one. And it could be that something called topological swelling is to blame, namely the metric scaling of equilateral random polygons and equilateral random unknots are different. Equilateral random polygons are very, very compact. They're in the random walk university class with metric exponent 1/2. But it's believed that when you fix the topology, so if you fix it to be an unknot, they swell up to the self-avoiding walk universality class. And so it could be, I don't want to say here, this is in contrast with what happens in self-avoiding polygons, namely self-avoiding polygons and self-avoiding unknots are the same metric. And so there's some weird thing going on here where conformations in the ambient equilateral random polygon space want to be compact, but the ones that we're sampling want to be bloated. And so are we really somehow, by doing this, restricting ourselves to a very small subset of the space, which is messing up the diffusion of the Monte Carlo? Or are these just bugs in my code? So what now? Much debugging and more debugging in punctuated progress, hopefully getting Nathan or Nick to code things up. Maybe need a better encoding of the polygon. Consider mixing in BFACF moves. try to get things working on Lattice, which requires some very careful tree and data structure hackery to make things work. And work continues very slowly. So many thanks to the organizers for today. And I just wanted to say 2 words about Richard at the risk of running extremely over time. I think that I first met Richard because I took a course in asymptotics with him maybe around 1994 as an undergraduate. Since then, I co-authored about 10 papers with him, including my first, and indeed, including my bestseller, as it were, was with Richard. I learned a lot about bijections, constant terms, generating functions, graphic design with him, learned a lot about teaching proof and logic, because we both taught proof and logic, both at him at Melbourne Uni, me at UBC. And we always enjoyed a very good grumble together. So this is a picture of Richard and I sitting in Saskatoon Airport, not entirely impressed with the world because we just missed a flight and we had to go and drink a beer in the bar, which wasn't so bad. And, we drank a lot of coffees together and, some beers, it should be said. And, it made a very big impact on my mathematics, on how I do it, how I present it, how I teach it. So, yeah, I'll miss you, Richard. I'm going to stop there. My apologies for going over.
Thanks, Andrew, for a lovely talk. And I'll just ask if there are any questions from our online participants to start with. No, not at the moment. Okay, any questions from our audience? No. In that case, I think since we are running a little bit over time, I think I will leave it there. But thanks very much, Andrew, for an excellent talk. And I just want to say, okay, do you want to have a word, Tony, or no? Oh, okay. No problem. So I just want to say a special thanks to the speakers in this session, but also to all our international speakers who are giving up their Sunday evenings and possibly staying up late into the night. So thanks very much for participating. And so that concludes the session. We'll have a break for a touch under 1 hour. So we'll be back here at 1:30 local time. And I hope to see everyone online as well after the break. Okay, thanks very much, everyone.